Hello and welcome to my presentation. My name is Heaven Asmaram and today we are going to be discussing question 4. The product of the reaction is a red solution due to the compound X, which is not the only product of the reaction. In order to study this reaction, solutions of X of different concentrations were examined spectrophotometrically. Part A. At what approximate wavelength would X absorb most strongly? X would absorb greatly at around 500 to 520 nanometers, which is in the green region over here. The color visible to us is complementary to the green light which is being absorbed. So if green light is being absorbed, then red light is being transmitted back to us, and that is what we were able to see. Part B. A stock solution that has 0.05 moles in X was used for dilutions as follows. Calculate the concentration of X for each solution. So this is the table with all the different solutions, the concentrations, buffer, water, and what we are calculating is the new concentrations. In order to calculate the new concentrations, we are going to be using the equation C1 times V1 equals C2 times V2, where C1 is the concentration of stock, V1 is the volume of stock, C2 is the final concentration of new solution, and V2 is the final volume of new solution. We are going to be looking at example 1 to figure out how to calculate the new concentration. In order to calculate new concentration, we are going to need to rearrange the equation to make C2 the variable. So C2 equals C1 times V1 over V2. So for solution 1, C1 is 0.05, which is the old concentration, V2, which is how much of 0.05 moles we used, C2, which is what we're trying to figure out, V2, which is 10, because if we add all the volumes together, it's going to be 2 plus 2 plus 6, which gives us 10. So if we plug that into the equation, we will get 0.05 times 2 over 10, which equals 0.01. And if we follow the same exact method for solutions 2, 3, and 4, we should get 0.02, 0.025, and 0.03. Part C. The absorbance of each solution is given in the table. If the path length is 1 centimeter, calculate the molar coefficient in meters squared mole to the minus 1. So the table given to us is here. They've given us the absorbance for each solution. So for solution 1 it's 0.02, solution 2 is 0.43, solution 3 is 0.55, and solution 4 is 0.67. In order to calculate molar coefficient, we are going to be using the equation A equals molar coefficient times length times concentration. So A is absorbance, L is the path length in centimeters, C is the concentration, and E is the molar absorption coefficient in meters squared mole to the minus 1. In order to calculate the molar coefficient, we are required to rearrange the equation so that the molar coefficient is the variable. So molar coefficient is equal to A over L times concentration. So if we take a look at the different solutions, solution 1 is 0.02, which is the absorbance, over the length, which is 0.01, as we need to divide 1 centimeter by 1,000 to get it in meters, times 0.01, which is the concentration that we got in the previous slide. This is then repeated for solution 2, solution 3, and solution 4. Solution 2 has an absorbance of 0.43 over 0.01 times the concentration, which is 0.02, which gives us 2,150 meters squared mole to the minus 1. Solution 3 is 0.05 over 0.01 times 0.025, which gives us 2,200 meters squared mole to the minus 1. And lastly, solution 4 is 0.67 over 0.01 times 0.03, which gives us 2,233 meters squared moles to the minus 1. Part D. The infrared spectrum of the compound X includes a strong peak at 1,640 centimeters to the minus 1. Due to a carbon double O oxygen bond in the molecule, assuming that this is a 12 carbon double bond O16, calculate the reduced mass in grams mole to the minus 1. So, in order to calculate the reduced mass, it requires the equation mass 1 times mass 2 over mass 1 plus mass 2, which the mass is given to us, so 12 for carbon and 16 for oxygen. So 12 times 16 and 12 plus 16 underneath, which gives us 6.86 grams over moles. But we are not finished. We need to get that number that we had before and divide it by Avogadro's constant to get 1.13 times 10 to the minus 23 grams per mole. Part II, the frequency of the signal in S-1. So the frequency is calculated by C times the wave number, and they've already given us the wave number, which is 1,640, and C is 3 times 10 to the power of 10, which gives us 4.92 times 10 to the 23. Part III, we are going to be calculating the force constant of the bond. In order to calculate the force constant, we must know the equation, which is half brackets K over mu close brackets to the power of a half. In order to find the force constant, we need to rearrange this whole equation to find K as the variable. To make K the variable, we need to rearrange the equation to 4 pi squared times v squared times mu. So if we plug in all the numbers that we got from the previous slides, we are going to get K equals 4 pi squared brackets 4 times 92 times 10 to the 13 close brackets squared, open brackets 1.13 times 10 to the minus 23 close brackets. We are dividing everything by 1,000 because we want to get it in kilojoules over second squared. So the answer we should get is 1079.9. Part IV. If one were to have done the calculation for 13C and 16O bond, what would not change in the calculation other than the equation and the value for pi? The wave number would not change and remain 1,640 centimeters to the minus 1 because the double bond is still between the carbon and the oxygen. So the peak will still remain the same. So even if the isotope of carbon changes, the frequency still remains the same and will still remain 4.92 times 10 to the 13 and